Natural state of things, water vapor is the most significant of these gases. These gases are called greenhouse gases. That name is a bit of a misnomer. The idea is that they function sort of like the glass in a greenhouse, but they don't really. The glass in a greenhouse keeps heated air from escaping the greenhouse in bulk. These gases keep radiation from escaping. That's a bit different than keeping heated air from escaping. The glass of a greenhouse does have some effect keeping infrared out from escaping, but that's a minor effect. Nevertheless, this term greenhouse gas is stuck, and this effect whereby greenhouse gases trap outgoing infrared radiation is called the greenhouse effect. And if you want to know a little bit more of the physics of why the greenhouse effect occurs, I'm not going to go into the details, and maybe a chemist would call this the chemistry of it. I'd call it the physics. If you look at the two molecules I just mentioned, water, H2O, and carbon dioxide, CO2, those are both triatomic molecules. Their molecules have 3 different atoms. And it turns out those triatomic molecules have many more ways to vibrate and rotate and move around than the simple diatomic molecules of oxygen and nitrogen. And many of those ways involve vibrations at the frequencies of infrared radiation. And that's why water vapor and carbon dioxide are greenhouse gases. They tend to be more complicated molecules than the simple molecules, oxygen and nitrogen, that make up most of the atmosphere. So these outgoing these atmospheric greenhouse gases absorb outgoing infrared radiation. They act like insulation. They keep it from, they keep that infrared radiation from getting out. They kind of trap it, and I'll describe this in a little more detail in just a moment. And the net effect, though, is that Earth's surface has to be at a higher temperature to get rid of that still 240 watts per square meter of radiation, of energy coming in, has to be at a higher temperature than it would be otherwise. And in the case of the natural greenhouse effect caused by naturally occurring water vapor and carbon dioxide in the Earth's atmosphere, the value of that effect, the amount by which it increases Earth's surface temperature, is about 33 degrees Celsius, roughly 59 or 60 degrees Fahrenheit. The Earth is warmer than that number we calculated, that 0 degrees Fahrenheit, by about 60 degrees Fahrenheit. It's warmer by than that minus 18 degrees Celsius by about 33 degrees Celsius. Gives it a temperature on the average of about 15 degrees Celsius or 60 degrees Fahrenheit. The Earth is warmer and more comfortable than it would otherwise be because of this naturally occurring greenhouse effect. So when I talk about the natural greenhouse effect, I'm talking about the effect of carbon dioxide and water vapor in absorbing outgoing infrared. Water vapor has the biggest effect, carbon dioxide comes second, in absorbing the outgoing infrared and therefore warming the surface to levels above what it would otherwise have. And so when I say the natural greenhouse effect is 33 degrees, I'm talking about something very specific. It's 33 degrees Celsius warming due to the presence of these greenhouse gases. And I think you'll agree that a planet at 60 degrees Fahrenheit average temperature, about 15 degrees Celsius average temperature, is a lot more comfortable than one that would have been at 0 degrees Fahrenheit, minus 18 degrees Celsius. It wouldn't have been an uninhabitable planet. I think life might have still formed, and some forms of life could still exist in some areas if there weren't the greenhouse effect, but it sure makes for a more habitable, enjoyable planet. So that's the essence of the greenhouse effect. And I'd like to spend a little bit more time describing not only the essence of the greenhouse effect, but also 3 different ways of understanding it in terms of scientific understanding. The simplest way is just to say the greenhouse gases act as an insulating blanket. They make it harder for energy to escape, and therefore the surface temperature is a little higher than it would be otherwise. And I think every citizen of an industrialized country that produces greenhouse gases ought to know at least that. A slightly more sophisticated way of looking at that is to consider an Earth system with greenhouse gases in the atmosphere. In an Earth system with greenhouse gases in the atmosphere, the infrared going out gets absorbed in the atmosphere, some of it. It heats up the atmosphere, and the atmosphere warms, and it does what any other warm system does, is it radiates energy out in the form of infrared in all directions. And for the atmosphere, all directions means upward and downward. And so the atmosphere returns to the surface some of the radiation that it got back from the surface originally. And consequently, the temperature of the Earth's surface has to be warmer than it would be otherwise in order for that energy to escape and keep the planet in energy balance. So if you had an Earth without greenhouse gases and you added greenhouse gases, that would momentarily drop the rate at which the Earth lost energy by infrared radiation. It would therefore heat up until there was again a balance established at what would be then a higher temperature. Perhaps the most sophisticated way of looking at all this is to consider what happens with the upper atmosphere. As the upper atmosphere is a cooler place than the surface and the lower atmosphere. And because of that, the upper atmosphere can't radiate as much energy as the surface can because it's cooler. And in particular, it can't radiate away all the energy that comes in as sunlight. And therefore, the Earth's surface has to get warmer and warmer in order to get some of that energy to escape despite the presence of the greenhouse gases. If for some reason the upper atmosphere were at the same temperature as the surface, there would be no greenhouse effect. And that's an important point that I hinted at in earlier lectures. In lecture 2, when I talked about the temperature change that's occurred recently in the stratosphere has actually cooled. A cool upper atmosphere and a warm surface are conditions needed for the greenhouse effect to occur. So that's the most sophisticated understanding of the greenhouse effect. And if you were to sort of diagram that, you would imagine that a little bit of infrared is escaping to space directly from the atmosphere, or a significant amount maybe, but not enough to balance the incoming sunlight. And you need some more additional infrared to escape from the surface. And because of the greenhouse gases, you need to have the surface very warm because it has to get a significant amount of energy out through the nearly opaque greenhouse gases. And you can begin to see that there are many ways that you might upset this kind of balance. You might upset this kind of balance by changing the amount of greenhouse gases in the atmosphere. You might upset this balance by changing the amount of sunlight. You might affect this balance by changing the composition of the greenhouse gases. There are many ways to upset this balance, but the point is it's a delicate balance, and it's established by a balance between the incoming sunlight and the outgoing infrared. Now, Earth's energy balance is actually a lot more complicated than what I've just described here. And I want to show you a diagram that gives you a sense of that complexity. Because I've only talked about sort of overall, in comes this much sunlight, out goes this much infrared. There's actually a lot of complicated interactions occurring, particularly between Earth's surface and its atmosphere. And to understand climate in a little more detail, we need to understand those interactions. So I'm going to take a look here at a diagram that describes some of the details of Earth's energy balance. And again, this is still averaged over the entire planet. We're not talking about, oh, what happens in Greenland, what happens in the tropics, what happens in Hawaii, what happens in the middle of the South Pacific Ocean. We're not talking about that. We're just looking at overall global averages, and already it begins to be fairly complicated and sophisticated. I was recently, by the way, at a climate conference that I go to every year, a conference that relates to the sun and its influence on climate. And every single speaker showed this diagram. And by the time the third or fourth speaker had showed it, there was a sort of, that became kind of a standing joke. But anyway, here's a diagram that depicts pretty much our best understanding of what the energy balance looks like in all its detail. Different scientists will give you slightly different values for some of the numbers that appear in this diagram. That's a matter of ongoing research, but the big picture we sort of understand. So there is in this diagram a very large arrow representing the incoming solar radiation. It's about 342 watts on every square meter. You may say, wait a minute, I thought you said 240. Well, I did, but 342 watts per square meter come in. Some of that energy, some of those watts, are reflected back into space before they ever get to play a role in the climate system. They're just sunlight that's reflected off into space. What are they reflected from? From the tops of clouds, which are highly reflective. If you've flown in an airplane and looked down on the clouds, they're very white and bright. That means sunlight is being reflected back into space. And if it goes back into space reflected, and sunlight, it never gets absorbed by the Earth atmosphere system, and it never plays a role in climate, except in a sense a negative role by not being there to provide energy for the Earth atmosphere system. So of that 342, about 77 of them are reflected by clouds and by particles and things in the atmosphere. About 30 of those watts are reflected by the surface, largely by ice sheets, snow, deserts, light-colored areas. And there's another way we could upset Earth's energy balance by changing the amount of, say, snow there is on the ground, or by deforesting an area and turning it into a desert. That would tend to make it absorb less sunlight, and more sunlight would be reflected. So that radiation, a total of 107 watts per square meter going off on the upper left of the diagram, doesn't play a role in the climate system. It doesn't get absorbed. Then what happens to the rest of the energy that's coming in, which amounts to about 235 watts per square meter? That's my 240 roughly that I was talking about before. Well, some of it, a small amount, about 67 watts per square meter, get absorbed in the atmosphere. They get absorbed in clouds. They get absorbed by volcanic dust. They get absorbed by dust that is blown off deserts. They get absorbed by particulate, air pollution, they get absorbed by things in the atmosphere and deposit their energy as heat in the atmosphere. Roughly half only of the incident solar energy, here it's 168 watts per square meter, only about half, a hair over half, actually gets absorbed and warms the surface directly. Some of it's already been reflected, some of it's got stopped in the atmosphere, roughly half of it gets to the surface, and its job there is to warm the surface. Absent any atmosphere, that 168 watts per square meter, but of course we've already had an atmosphere to reflect some of that, but if there were no other effects from the atmosphere, that would be sent off as infrared radiation to space, and the Earth's surface temperature would be whatever it needed to be to radiate that 168 watts per square meter. But we have the greenhouse gases in the atmosphere, and on the right side of the diagram you see the effect of the greenhouse gases. You see that the greenhouse gases are radiating back to the surface. 324 in this particular diagram watts per square meter back to the surface. Of course everything's in balance, so the surface is radiating most of that back away again. And most of it gets stuck in the atmosphere, and it's almost a cycling if you want to think of it that way. It's not building up, everything's in a steady balance. But there's a small fraction of that depicted by an arrow that goes all the way from the surface up to the top of the atmosphere, about 40 watts per square meter. It's called the atmospheric window, and that's the small amount of energy that's able to escape from the surface all the way up to space as infrared radiation, because the greenhouse gases are not 100% opaque. If they were 100% opaque, we'd be in big trouble. But they're not, and that atmospheric window allows a small amount of energy to escape, and it's enough to keep everything in balance. But the point is, because of those greenhouse gases radiating energy back downward, the Earth's surface has to radiate a lot more energy upward, and because the radiation increases with temperature, that means the temperature has to be a lot higher than it would be otherwise. How much higher? That 33 degrees Celsius, about 60 degrees Fahrenheit of the natural greenhouse effect. So that's the picture, and if you had to look at this diagram and say, where's the greenhouse effect? It's in that upward and downward, particularly in that downward flowing arrow representing back radiation that's flowing down from the greenhouse gases in the atmosphere to the surface. Of course, those greenhouse gases are also sending some radiation off into space. Now, this isn't the whole picture. And the reason it isn't the whole picture is because there are other important processes that transport energy between Earth and atmosphere. And in particular, they consist of convection, a process whereby heated air gets less dense and rises, and it takes with it the energy that it contains by virtue of being hotter. That's in this diagram called thermals. When you see a day when there are a lot of little puffy cumulus clouds forming in the atmosphere, they typically form at the top of thermals. Warm air has heated, it's risen, and it's cooled a bit as it rises, and when it reaches the point where the moisture condenses, you get a cloud at the top of that rising thermal. But what that thermal has done is transport energy into the atmosphere, and a significant flow of energy occurs because of those thermals, the actual bulk transport of heated air into the atmosphere. A more significant flow from the surface into the atmosphere is in what's called latent heat. That's the energy that's associated with water being in the gaseous state instead of the liquid state. So when water evaporates from the surface of the ocean and that moisture-laden air is transported into the upper atmosphere, it's carrying with it that moisture. And it carries with that moisture, in the form of vaporous water, it carries with it the energy that it took to turn liquid water into water vapor. And if that water vapor recondenses into liquid water and falls as precipitation, that energy becomes available as heat. And it's that energy that, for example, in the extreme case, drives hurricanes. It's largely the energy associated with the evaporation of water. Of course, that was ultimately solar energy, but in this case, the mechanism for transferring the energy into the atmosphere is not radiation, not the sending out of infrared radiation because things are hot, but rather the transfer of moist air containing the so-called latent heat associated with the evaporated water. So the energy balance of Earth is a complicated system, and we need to understand the details of that system to understand climate. But the big picture for us here in this lecture is that energy balance will occur, and it will occur naturally, and it will occur when the rate at which energy comes into a system, particularly the Earth, is equal to the rate at which energy goes out from the system. And for Earth, the energy goes out entirely to space by infrared radiation, but there are transfers between the Earth and the atmosphere, some of them by radiation, some of them by these convective effects, the thermals and the latent heat. that move energy back and forth between Earth and atmosphere. And the big important one for our purpose is the effect of the greenhouse gases in absorbing the infrared, sending some of them back to the surface, and making the Earth warmer than it would be otherwise by about 33 degrees Celsius or 60 degrees Fahrenheit, the natural greenhouse effect.